52 AD, 90 kilometers outside Rome, the Apennine Mountains. Chief engineer Nonius Datus takes a deep breath, staring at the simple wooden tool in his hand. Before him lie deep valleys that seem impossible to cross, solid rock that must be pierced, and a void stretching for miles. Have you ever stopped to consider what it actually takes to move a single drop of water across 90 kilometers? No pumps, no electricity, no pressure tanks. There is only one force: gravity. Nonius's mission is the greatest gamble in history. If he miscalculates the tunnel's gradient by just a few centimeters per kilometer, the water will either flow too fast and burst the tunnels, or come to a halt and never reach Rome. A single centimeter of error means 1 million people dying of thirst. A single centimeter of error means the end of the empire. So how did the Romans achieve this flawless gradient through the heart of mountains 2,000 years ago using nothing but water and wood, a feat that modern engineers struggle with even using laser scanners? If you are ready to learn how Rome conquered the world, not with the sword, but with water, sit back, because this story is not a victory of stone, but a victory of intellect. But before we follow Nonius into those mountains, we need to understand why Rome was so desperate for water in the first place. Because this was not just about convenience, this was about survival. The year is 312 BC. Rome is not yet an empire. It is a republic, growing faster than anyone expected. The population has just crossed 200,000, and there is a problem. A massive, life-threatening problem that no one wants to talk about publicly. The Tiber River is dying. Not literally dying, but becoming unusable. For centuries, Romans have drawn water from the Tiber. They have bathed in it, washed their clothes in it, even drunk from it. But now, with 200,000 people living in the city, the river has become a sewer. Imagine this. Every morning, thousands of Romans relieve themselves into clay pots. These pots are then emptied into the streets. Rain washes the waste downhill, and where does it all go? Directly into the Tiber. The smell alone is unbearable, but worse than the smell is the sickness: dysentery, typhoid, cholera. Diseases spread through the water like wildfire. Children die first, then the elderly, then the soldiers. A city cannot function when its people are constantly sick. An army cannot march when its soldiers are doubled over with stomach cramps. And an empire cannot expand when its capital city smells like an open latrine. The Senate knows this. They gather in emergency session. The topic is water, or rather, the lack of clean water. Senator Appius Claudius Caecus stands before them. He is old, nearly blind, but his mind is sharp as ever. "Senators," he begins, his voice cutting through the murmuring crowd. "Rome is dying, not from war, not from famine, from thirst." The room falls silent. Everyone knows he is right, but no one wants to admit it. "The Tiber River is poisoned," Appius continues. "We have turned our sacred river into a cesspool, and now we are paying the price. Our children drink death. Our soldiers grow weak. Our enemies laugh at us." One senator stands. "What do you propose, Appius? We cannot simply create water from nothing." Appius smiles. It is a cold smile, a calculating smile. "We do not need to create water. We need to bring it from the hills, from the mountains, from springs so pure that even the gods drink from them." Another senator scoffs. "The nearest clean spring is 40 kilometers away. How do you propose we bring water from there? Carry it in buckets." "No," Appius replies. "We will build a channel a stone channel that runs from the spring to Rome. The water will flow by itself, guided by gravity, never stopping, never slowing, day and night, year after year, the water will come. The room erupts in laughter. It is absurd, impossible. No one has ever built anything like that. The engineering challenges alone are overwhelming. How do you maintain a consistent gradient over 40 kilometers? How do you cross valleys? How do you tunnel through solid rock? But Appius does not laugh. He waits for the noise to die down, then he speaks again, quieter this time, but with iron conviction. Laugh if you want, mock me if it pleases you, but know this: in 10 years, Rome will have 1 million people. In 20 years, 2 million. And if we do not bring water to this city, those millions will die, or they will leave, and Rome will become a ghost town, remembered only as the city that grew too fast and collapsed under its own filth. The laughter stops, because everyone in that room knows he is right. Rome is growing at an impossible rate. Conquered territories are sending tribute. Trade routes are expanding. People are flooding into the city from all over the Italian peninsula, seeking opportunity, wealth, and safety. But growth requires infrastructure, and the most basic infrastructure of all is water. One senator, more practical than the others, asks the crucial question: how much will this cost?
Appius does not hesitate. Everything. Everything? Yes, every coin in the treasury, every slave we own, every engineer we can hire. This will be the most expensive project in Roman history, but it will also be the most important. The Senate debates for hours. Some argue it is too expensive. Others say it is too risky. What if the channel breaks? What if the water stops flowing? What if enemies poison the water at the source? But in the end, the decision is obvious. Without water, Rome has no future. With water, Rome can grow forever. The vote is called. The aqueduct project is approved, and Appius Claudius Caecus, the nearly blind senator, is put in charge of building it. They will call it the Aqua Appia, the first Roman aqueduct, the beginning of an empire built not on swords, but on water. But Appius is not a fool. He knows the Senate's support is fragile. If this project fails, he will be ruined, his family will be disgraced, his name will become a joke. He needs the best engineers Rome has. He needs surveyors who can measure elevation with impossible precision. He needs workers who can dig through solid rock. And most importantly, he needs someone who understands water, someone who knows how it flows, how it bends, how it can be controlled. That someone is Nonius Datus. Nonius is young, only 28 years old, but he has already made a name for himself as a surveyor. He can measure distances with accuracy that seems almost magical. He can read terrain like others read books, and he understands something fundamental about water that most people do not. Water is lazy. It always takes the easiest path. It flows downhill because gravity pulls it. But if you create the right conditions, if you give it a channel with the perfect gradient, water will flow exactly where you want it to go. Not too fast, not too slow, just right. Appius summons Nonius to his villa. The old senator sits in darkness. His eyes no longer work, but his mind is sharper than ever. Nonius, Appius says, I am giving you an impossible task. I specialize in impossible tasks, Senator, Nonius replies with a slight smile. Good, because what I am about to ask you will determine the future of Rome. Appius explains the project. 40 kilometers of channel, most of it underground to protect the water from the sun and from enemies. a gradient so precise that the water flows steadily without ever stopping or overflowing. Can it be done? Appius asks. Nonius does not answer immediately. He thinks, calculates, visualizes the terrain in his mind. 40 kilometers, underground, through rock and clay and sand, maintaining a gradient of less than half a meter per kilometer. It is insane. It has never been attempted, but Nonius has seen enough failed projects to know what is truly impossible and what is merely difficult. Yes, he finally says, it can be done, but it will take time and precision and luck. Appius nods. You will have all the time you need, all the resources Rome can provide. But understand this, if you fail, Rome dies, and your name dies with it. Nonius feels the weight of those words. 1 million people depending on him. The future of the greatest republic in history resting on his ability to calculate gradients and dig tunnels. He takes a deep breath. When do I start? Now, Appius says. Pack your tools, gather your team. Tomorrow you leave for the Anio Valley. Find the spring, measure the elevation, calculate the route, and then come back and tell me if Rome has a future. That night, Nonius cannot sleep. He lies awake, staring at the ceiling, thinking about water, how it flows, how it bends, how it can be controlled. He thinks about the tools he will use. The chorobates, a 6-meter wooden leveling instrument. The groma, a surveying cross for measuring right angles. Simple tools, primitive by modern standards, but in the right hands, capable of incredible precision. And he thinks about the challenge ahead. 40 kilometers through unknown terrain, valleys to cross, hills to tunnel through, rock to break, clay to dig, all while maintaining a gradient so subtle that a single error could doom the entire project. As dawn breaks, Nonius gathers his team. 5 surveyors, 10 slaves for carrying equipment, and a simple mission. Find the water, measure the path, make it possible. They leave Rome as the sun rises, walking north toward the Apennine foothills. Behind them, the city continues its daily chaos. Merchants shouting, children playing, senators arguing. No one notices the small group of men leaving the city gates. No one realizes that these men are about to change history. Because water, it turns out, is not just about survival. It is about civilization itself.
3 days later, the Anio Valley, 40 kilometers northeast of Rome. Nonius and his team stand at the edge of a crystal-clear spring. Water bubbles up from deep underground, flowing over smooth stones, creating a sound like music. This is it. This is the source. Nonius kneels beside the water and cups his hands. The water is ice cold, even in the summer heat. He drinks. It tastes clean, pure, nothing like the murky, foul-tasting water of the Tiber. How much water flows here? Asks Marcus, one of his surveyors. He is older, more experienced, and clearly skeptical of this entire project. Nonius watches the spring carefully. He estimates the flow rate by observing how fast the water moves, how wide the stream is, how deep. It is not scientific, not precise, but it is good enough. Enough, Nonius says. Enough for 200,000 people, maybe more. Marcus snorts. If we can get it there. We will get it there, Nonius replies firmly. But Marcus is not wrong to be skeptical. Between this spring and Rome lies 40 kilometers of brutal terrain. Hills, valleys, rocky outcrops, dense forest, and most challenging of all, the need to maintain a consistent downward slope the entire way. Nonius pulls out his chorobates.
It is a simple device, really. A wooden beam 6 meters long with vertical posts at each end. Between the posts hangs a plumb line, and on top of the beam sits a shallow channel that can be filled with water. When the water sits level in the channel, the beam is perfectly horizontal. By making tiny adjustments and measuring the height difference between 2 points, Nonius can calculate the gradient with remarkable precision. But doing this over 40 kilometers through forests and hills and unknown terrain is another matter entirely. "We start measuring," Nonius announces. "From here to Rome. Every 100 meters we take a reading. We mark the elevation, we calculate the gradient." "That will take months," Marcus protests. "Then we better start now." The work begins. It is tedious, exhausting. One man holds the Corybates steady while another measures the vertical drop using a measuring rod. A third man records the numbers on a wax tablet. Then they move forward another 100 meters and repeat. Hour after hour, day after day, the sun beats down, mosquitoes swarm. The slaves carrying equipment grow tired and irritable. But Nonius does not stop. He cannot stop, because every measurement matters. On the 5th day, they encounter the first major problem. A deep valley cuts across their path. The valley is at least 30 meters deep and 200 meters wide. Building a bridge to carry water across this gap would be impossibly expensive.
Marcus sees the valley and shakes his head. "We have to go around, find another route." But Nonius is thinking, there might be another way, a way that does not require a massive bridge, but it would require something else, something risky. "What if we do not go over?" Nonius says quietly. "What do you mean?" "What if we go under? We dig a tunnel through the hillside, bring the water underground around the valley." Marcus looks at him like he has lost his mind. Tunnel through solid rock? That will take years. Not if we dig from both sides simultaneously. This is the key insight. If they can calculate the exact angle and elevation, they can start digging from opposite sides of the hill and meet in the middle. It cuts the construction time in half, but it also doubles the risk. If the calculations are wrong, if the 2 tunnels do not meet, the entire project fails. Marcus is silent for a long moment. Then he nods slowly. "It is insane, but it might work." "It will work," Nonius says, with more confidence than he feels. They spend 3 days surveying around the valley, calculating angles, measuring elevations. Nonius fills tablet after tablet with numbers, geometry, trigonometry, calculations that would make most men's heads spin. Finally, he has it, the exact angle, the precise elevation, the point where the 2 tunnels will meet, deep inside the hill. "We dig here," he says, marking the spot with a stone, "and here on the other side. If my calculations are correct, we will meet in the middle in 6 months." "And if your calculations are wrong?" Marcus asks. Nonius does not answer, because they both know what happens if he is wrong. The project fails. Rome stays thirsty, and Nonius becomes the engineer who promised the impossible and delivered nothing. That night, alone in his tent, Nonius reviews his calculations again and again and again, looking for errors, looking for mistakes. The margin for error is so small, just a few centimeters over several hundred meters of tunnel. 1 centimeter of error means the tunnels miss each other. 1 centimeter means failure. 1 centimeter means the end of everything. He closes his eyes and whispers a prayer to Minerva, goddess of wisdom and engineering. "Guide my hand, guide my mind. Let the numbers be true." Tomorrow, they will mark the route back to Rome, and then the real work begins. The digging, the tunneling, the building, the impossible task of moving water across 40 kilometers using nothing but gravity and stone. Rome is counting on him. 1 million people are counting on him. The future of civilization is counting on him. No pressure.
6 months later, underground. Darkness so complete that torchlight seems like a feeble joke against it. The air is thick with dust and the smell of sweat. The sound of iron striking stone echoes endlessly. 2 teams of workers are digging toward each other through solid rock. One team started on the north side of the hill, the other on the south. They have been digging for 180 days straight, and they still have not met. Nunez stands in the northern tunnel, holding a torch, listening. He presses his ear against the rock face ahead. Nothing, just silence and stone. "Anything?" asks Marcus, covered head to toe in rock dust. "Not yet." "They should be close by now, if your calculations were correct." That word, if, it hangs in the air like an accusation. Nunez rechecks his measurements for the 1,000th time. According to his calculations, the 2 tunnels should meet within the next 10 meters. But 10 meters of solid rock might as well be 10 kilometers when you cannot see through it. What if he made a mistake? What if the angle was wrong? What if the southern team is digging 5 meters to the left, and the 2 tunnels will pass each other like ships in the night, forever separated by stone? The workers keep digging. 20 men with iron picks hammering at the rock face. Progress is measured in centimeters per day. The rock here is limestone, thank the gods. If it were granite, they would still be halfway through. Every meter they advance, Nunez measures again, checking the gradient, checking the angle, obsessively verifying that they are still on course. The gradient must remain constant, 0.4 meters drop per kilometer. Too steep, and the water will flow too fast, eroding the tunnel walls. Too shallow, and the water will stagnate, allowing algae and disease to breed. This is the secret that most people do not understand about Roman aqueducts. It is not about building impressive arches. It is about maintaining an almost invisible slope over vast distances. The arches that everyone admires are just the solution to crossing valleys. The real engineering marvel is underground, invisible, eternal. On the 187th day, something changes. The workers hit a different kind of rock, softer, more porous. The picks bite deeper. Progress accelerates. "We are through the hard layer," Marcus reports. "The southern team must be close." Nunez presses his ear to the rock again. This time, he hears something, faint, distant, but unmistakable. The sound of picks striking stone from the other side. "They are there. They are right there," he whispers. The work intensifies. Both teams can hear each other now through the thinning rock wall. The northern team hammers faster. The southern team responds with their own rhythm. It becomes a race, a competition. Who will break through first? 3 days later, a pick strikes through, a tiny hole. Light from the southern tunnel's torches suddenly pierces through. The northern workers erupt in cheers. They did it! The tunnels met. Not 5 meters apart, not even 1 meter. The 2 tunnels aligned within 30 centimeters of each other. An engineering miracle achieved with nothing but wooden tools, wax tablets, and mathematics. Marcus claps Nunez on the shoulder. "You did it! You actually did it!" But Nunez does not celebrate, not yet. Because meeting
is only half the battle. Now they need to verify the gradient. If one tunnel is higher than the other, water will not flow properly. There will be a step, a discontinuity, a failure point. He sets up his Corabates inside the tunnel, measuring the elevation of both tunnels at the breakthrough point. His hands shake slightly as he adjusts the water level in the measuring channel. The entire project depends on this moment. 6 months of digging, hundreds of workers, thousands of man-hours, all come down to this single measurement. He reads the water level, checks it again, looks up at Marcus with an expression of disbelief. "Well," Marcus demands, "what's the difference?" 2 centimeters, Nunius says quietly. The southern tunnel is 2 centimeters lower. 2 centimeters over several hundred meters of tunnel, an error rate of less than 0.01%, with primitive tools and no way to see through solid rock. Marcus laughs. It is a laugh of relief, of joy, of absolute astonishment at what they have accomplished. 2 centimeters, that is nothing. We can adjust the floor, smooth it out. Yes, Nunius agrees, finally allowing himself to smile. Yes, we can. The workers widen the breakthrough, connecting the 2 tunnels fully. For the first time, a person can walk from one side of the hill to the other without climbing over it. A passage through solid rock, carved by human hands, guided by human minds. But this is just one tunnel, one small section of a 40-kilometer system. And ahead lie bigger challenges, deeper valleys, harder rock, and the greatest engineering puzzle of all. How do you cross a valley too deep for arches and too wide for tunnels? The answer will require something Romans have never attempted before. Something that will make even this tunnel breakthrough seem simple.
1 year into the project, the Martian Valley. Nonius stands at the edge of a cliff, looking down into a gorge that drops 60 meters straight down. The valley is 400 meters wide. Building arches to span this would require a structure taller than any building in Rome. The cost would be astronomical. The engineering, nearly impossible. "We cannot cross this," Marcus says flatly. "It is too deep, too wide. Even if we had unlimited funds, the arches would collapse under their own weight." Nonius says nothing. He is thinking, calculating. There is another way, a way that does not require arches at all. But it requires something that sounds insane, something that defies common sense. "What if we do not go over?" he finally says. "We already discussed tunneling. The valley is too wide. It would take 10 years to tunnel that far." "I am not talking about tunneling through the hill," Nonius says slowly. "I am talking about going down into the valley and then back up the other side." Marcus stares at him. "You want to send water downhill and then expect it to climb back up? Water does not flow uphill, Nonius. Even a child knows that." "Water does not flow uphill," Nonius agrees, "but pressure can push it uphill." He kneels and draws a diagram in the dirt with a stick, a simple U shape. This is called an inverted siphon. We build a sealed pipe that goes down one side of the valley and up the other. We fill it completely with water, no air. The water at the top of one side pushes down with pressure. That pressure forces the water up the other side. Marcus studies the drawing. That is the principle of connected vessels. Exactly. If we seal the pipe perfectly, if we make it strong enough to withstand the pressure at the bottom, water will flow through the valley without needing arches. What kind of pipe can withstand that much pressure? Marcus asks. At 60 meters depth, the pressure will be immense. Lead, Nonius says. We cast lead pipes, thick ones, strong enough to hold the pressure. Lead pipes 400 meters long? Do you know how much that will cost? How much lead that will require? Less than building a 60-meter tall aqueduct bridge, Nonius replies. And it will work. It has to work. But even as he says this, doubt gnaws at him. This technique has never been attempted on this scale. Small fountains use inverted siphons, garden water features, but to move Rome's entire water supply through a pressurized pipe system buried in a valley? That is something else entirely. The Senate will think he is mad. Appius will question whether he knows what he is doing. And if the pipes burst under pressure, if the system fails, the entire aqueduct project collapses. We need to test it first, Marcus says flatly. Build a small version. Prove it works before we commit. Nonius nods. Agreed. We build a test system, 1/10 scale. If it works, we build the real thing. They spend 2 months constructing the test, a miniature inverted siphon using clay pipes instead of lead. They seal the joints with resin. They bury it in a small ravine. Then they open the valve and watch. At first, nothing happens. The water fills the downward pipe slowly. Air bubbles rise. The system gurgles and hisses. For a terrible moment, Nonius thinks it has failed. Then suddenly, water bursts from the top of the opposite side. It sprays into the air, driven by the pressure from below. The force is incredible. The water shoots 2 meters above the pipe opening before settling into a steady flow. It works. The physics works. The inverted siphon works. Marcus is speechless. By Jupiter, it actually works. Now we build the real one, Nonius says, and we pray the lead pipes hold. The lead casting begins. They need pipes 30 centimeters in diameter and thick enough to withstand 60 meters of water pressure. The metal workers complain. They have never cast pipes this thick. The lead alone costs a fortune. But Nonius insists. He calculates the wall thickness needed. He supervises every casting personally. Because if even one pipe is weak, if even one joint fails, pressurized water will burst through and flood the valley. Workers will die. The project will fail. It takes 8 months to manufacture all the pipes. 8 months of constant work. The lead is melted in massive furnaces, poured into molds, cooled, tested. Any pipe with the slightest imperfection is melted down and recast. Finally, they are ready. The pipes are transported to the valley and laid carefully down one side and up the other. Each joint is sealed with molten lead. Each connection is inspected 3 times. Nonius stands at the top, hand on the valve that will release water into the system. Marcus is at the bottom, 60 meters below, ready to check for leaks under pressure. "Are you ready?" he shouts down. "Ready." Marcus's voice echoes up from the depths. Nonius opens the valve. Water begins to flow. Down, down, down into the valley. The pipes groan, metal creak. Everyone holds their breath. At the bottom, Marcus watches the pipes fill. The pressure builds. He can hear the metal straining. One joint begins to weep, dripping water, but it holds. The water reaches the far side, begins climbing, rising against gravity, pushed by pressure from behind. Higher, higher. Nonius watches from above, heart pounding. Will it reach the top? Or will the pressure be insufficient? Will the pipes burst? Will the system fail? The water climbs and reaches the outlet and flows. Steady, strong, impossible, but real. They did it. They moved water through a valley without arches, using nothing but physics, lead, and audacity. Rome has its water, but the system still needs one more thing to be perfect: a way to keep the water clean.
2 years into construction, 15 kilometers outside Rome, Nonius stands inside a massive underground tunnel, examining the walls with a critical eye. The tunnel is beautiful, perfectly carved. The gradient is flawless. Water will flow through here for centuries. But there is a problem most engineers would never even think about. The water is dirty, Nonius says. Marcus looks confused. What do you mean dirty? It comes from a pure mountain spring. Yes, but after flowing 40 kilometers through tunnels, what do you think happens? Sediment washes in, leaves fall through ventilation shafts, dust settles. By the time the water reaches Rome, it'll be cloudy, contaminated. So we filter it, Marcus suggests. With what? If we put grates across the channel, they will clog and stop the flow. We need something else, something that cleans the water without blocking it. Nonius has been thinking about this problem for months, and he has found the answer in nature itself. Rivers do not stay dirty, they clean themselves. How? By slowing down. When water moves slowly, sediment settles to the bottom. The heavier particles sink first, then the lighter ones. Eventually, only the cleanest water remains on top. This is the principle they need to harness. We build settling tanks, Nonius announces. Every 5 kilometers, we expand the tunnel into a large chamber. The water enters the chamber and spreads out. The flow slows dramatically. Sediment settles to the bottom. Clean water exits from the top and continues to Rome. How large do these chambers need to be, Marcus asks. Big enough that water spends at least 2 hours inside. That gives enough time for all but the finest particles to settle. They call these chambers piscina limaria, cleaning pools. Each one is 15 meters long, 8 meters wide, and 3 meters deep. They are carved into the bedrock at strategic points along the aqueduct route. The design is ingenious. Water enters near the bottom on one side. It spreads across the chamber, slowing to almost a standstill. Sediment settles to the bottom. Clean water exits from the top on the opposite side, continuing its journey to Rome. But the settling tanks have another problem. They will fill with sediment over time. Eventually, they will need to be cleaned. But you cannot simply drain an aqueduct that supplies water to 1 million people. We need access, Nonius says. Manholes, stairs leading down into each settling tank, so maintenance workers can climb in and shovel out the sediment without stopping the water flow. Marcus nods. And the walls? Stone is porous. Water will seep through and weaken the structure over time. This is another critical problem. Most stone allows water to seep through slowly. Over years, this seepage can erode the structure from within. They need a waterproof lining, something that seals the stone completely. The answer is opus sininum, a special Roman concrete made from crushed tile, lime, and volcanic ash. When applied to stone surfaces, it creates a hard, waterproof coating that can last for centuries. We line every tunnel, every chamber, every surface the water touches with opus sininum, Nonius instructs. 2 layers, each layer 3 centimeters thick. No gaps, no weak points. The work is meticulous. Slaves mix the opus sininum in large wooden troughs.
The mixture must be perfect. Too wet and it will not adhere. Too dry and it will crack. Workers apply it to the tunnel walls with wooden trowels, smoothing it carefully. The smell is distinctive. The lime burns their nostrils. The crushed tile gives it a distinctive red color. But once it hardens, it becomes nearly as strong as the stone itself and completely waterproof. Nonius runs his hand over a finished section. The surface is smooth, slightly glossy, perfect. Water will flow over this surface for 1,000 years without eroding it. But there is one more element needed: ventilation shafts. Every 80 meters, they dig vertical shafts from the surface down to the tunnel. These serve multiple purposes. They allow air to circulate, preventing the buildup of dangerous gases. They provide access points for maintenance, and they release pressure, preventing airlocks from forming in the system. Each ventilation shaft is covered with a heavy stone lid to prevent debris from falling in, and to prevent sabotage, because Nonius knows that Rome has enemies, and those enemies would love nothing more than to poison Rome's water supply. Every access point is a vulnerability, Nonius tells Marcus. We guard them, we seal them, we make it impossible for anyone to tamper with the water. 3 years into construction, the aqueduct is nearly complete. 40 kilometers of tunnel, mostly underground, 8 settling tanks, 50 ventilation shafts, lead pipes spanning deep valleys, and all of it maintained at a precise gradient of 0.4 meters per kilometer. It is time for the final test, the moment they have been working toward. They will open the valve at the source and see if water reaches Rome. If the gradient is correct, if the system holds, if the impossible becomes real. Everyone gathers at the spring. Nonius's hand rests on the valve. One turn, and water begins its 40-kilometer journey. One turn, and history changes. He looks at Marcus. Ready? Ready. Nonius opens the valve.
The water flows, slowly at first, filling the channel at the spring, then faster as gravity takes hold. The sound of rushing water echoes through the first tunnel section. Workers cheer, but Nonius does not celebrate yet. How long until it reaches Rome? Marcus asks. Nonius calculates in his head. 40 kilometers at a flow rate of approximately 1 meter per second. 11 hours, maybe 12. By midnight, water should arrive at the distribution tank in Rome. 11 hours of waiting. 11 hours of anxiety. 11 hours wondering if somewhere along those 40 kilometers something will fail. A tunnel will leak. A pipe will burst. The gradient will be wrong and water will stop flowing. Nonius decides to follow the water. He and Marcus mount horses and begin riding along the aqueduct route, checking each inspection point. At the first settling tank, water is already arriving, spreading across the chamber, beginning its slow dance of sedimentation. "It is working," Marcus says with relief. "So far," Nonius replies cautiously. They ride to the first inverted siphon, the one crossing the deep valley. This is the most dangerous section. If the lead pipes are going to fail, it will happen here under maximum pressure. Nonius climbs down into the valley to the lowest point where the pipes are buried. He presses his ear against the ground. He can hear it. The rush of water under pressure, moving through the lead pipes 6 meters underground. The sound is strong, steady. No indication of leakage or stress. At the opposite side of the valley, they check the outlet. Water should be climbing up through the pipes now, pushed by pressure from below. But will it reach the top? Or will air pockets form, creating blockages? They wait. 10 minutes. 20. Then suddenly, water bursts from the outlet pipe with tremendous force. It works.
The inverted siphon works perfectly. "By all the gods," Marcus whispers, "we actually did it!" They continue following the water's path. Each settling tank shows water arriving, spreading, beginning to clarify. Each tunnel section shows steady flow at exactly the predicted rate. The gradient is perfect. The engineering is flawless. As sunset approaches, they reach the outskirts of Rome, the final section of aqueduct, the distribution tank where water will be divided among different parts of the city. A crowd has gathered. Senators, engineers, curious citizens. Everyone wants to witness this moment. Appius Claudius Cacus is there, the senator who started this entire project. He is even older now, completely blind, but his hearing is sharp. "Nonius," he calls out, "is the water coming?" "Yes, Senator, it should arrive within the hour." "Should?" Appius asks with a slight smile. "Will," Nonius corrects himself. "It will arrive within the hour." The crowd grows. Torches are lit as darkness falls. The distribution tank sits empty, waiting. Its stone walls are lined with opus signum, waterproofed and ready. Multiple outlet pipes lead from the tank toward different districts of Rome. The Senate has already decided how the water will be distributed. First priority goes to public fountains, where ordinary citizens can collect water for free. Second priority to public baths. Third priority to wealthy homes that can afford to pay for private connections. Everyone waits, watching the inlet pipe, listening for the sound of approaching water. The crowd falls silent. Even the children stop playing. Then, someone hears it, a distant rumble. The sound of water rushing through the final tunnel section, getting closer, closer. The rumble becomes a roar. And then it arrives. Water explodes into the distribution tank with such force that it splashes up the walls. Clean, clear, perfect. The crowd erupts in cheers. People are crying, embracing, celebrating. Rome has water. Clean water. Unlimited water. Water that will flow day and night, year after year, forever. Appius makes his way to Nonius, guided by an attendant. The old senator reaches out and grabs Nonius by both shoulders. "You did it," he says, his voice thick with emotion. "You brought water to Rome." "We did it, Senator. All of us." "No," Appius says firmly. "This was your mind, your calculations, your vision. Rome will remember you for 1,000 years." But Nonius knows the truth. Rome will not remember him. History will remember the aqueduct, but not the engineer who designed it. The stone and water will endure, but his name will fade. And somehow, that does not bother him, because the work itself is the monument. The water flowing is the legacy. Within days, public fountains across Rome begin operating. Citizens line up with clay jugs, filling them with clean water. No more drinking from the polluted Tiber, no more sickness, no more disease spreading through contaminated water. The public baths open next, massive structures where Romans can bathe in clean, flowing water. This is not just about hygiene, this is about civilization itself. Bathing becomes a daily ritual, a social activity, a defining characteristic of Roman life. And the city grows. With unlimited clean water, there is no limit to Rome's population. Within a generation, the city reaches 500,000 people, then 750,000, then 1 million. The largest city in the ancient world, all made possible by water flowing through stone channels carved through mountains. But Nonius knows this is just the beginning. One aqueduct is not enough for a city of 1 million. They will need more, many more. Over the next 500 years, Rome will build 11 major aqueducts, some even more ambitious than this first one. longer, higher, more complex, but they will all follow the same principles that Nonius established here. Precise gradient, underground protection, settling tanks, waterproof lining, inverted siphons. The engineering template is set.
50 years later, a new generation of Roman engineers stands before the most ambitious aqueduct project ever conceived, the Aqua Claudia. It will bring water from springs 69 kilometers away. And unlike the earlier aqueducts that stayed mostly underground, this one will require something spectacular, something visible, something that will declare Roman engineering supremacy to the world. Arches. Massive stone arches stretching across the landscape. The chief engineer, a man named Quintus, studies the terrain. For most of the route, the aqueduct can remain underground, following Nonius's proven design. But there is one section, a broad valley 15 kilometers long, where the ground drops away completely. They cannot tunnel under it, the valley is too wide, and an inverted siphon would require lead pipes stretching for kilometers, which is impractical and expensive. They must build above ground, on arches, tall arches that will carry water across the valley like a stone river suspended in air. "How high?" asks his assistant. Quintus calculates. The gradient must remain consistent, 0.3 meters per kilometer for this aqueduct. To maintain that gradient across the valley, the arches must reach 27 meters at their highest point, 9 stories tall, higher than most buildings in Rome. 27 meters, Quintus announces, and they must support not just their own weight, but also the weight of the water channel on top, plus the water itself flowing through. The assistant looks pale. No one has ever built arches that high. They will collapse. They will not collapse, Quintus says, with confidence he does not entirely feel. Because we will use the same principle that holds up the Colosseum, multiple tiers, each tier supporting the one above. The design takes shape. The lowest tier will have massive, thick arches, heavy, strong, built from huge blocks of travertine stone. These will bear the greatest load. Above them, a second tier of lighter arches, and in some sections, even a third tier at the top, carrying the actual water channel. The arches themselves follow a perfect semicircular shape. This is critical. The semicircle naturally distributes weight evenly down both sides to the supporting pillars. Any other shape would create stress points where the structure would fail. Construction begins. Thousands of workers, slaves mostly. Some are prisoners of war. Others are born into slavery. They quarry the stone, they transport it, they cut it, they lift it into place using wooden cranes and pulleys. The work is dangerous. Men fall from scaffolding. Stones slip and crush workers below. Each tier built requires wooden frameworks to support the stones until the keystone, the final wedge-shaped stone at the top of each arch, is placed. Once the keystone locks in, the arch becomes self-supporting and the wooden framework can be removed. But that moment, placing the keystone, is terrifying. If the measurements are wrong, if the angle is off by even a degree, the arch will collapse when the framework is removed. Workers have died when arches failed. Entire sections have crumbled, killing dozens. Quintus personally oversees each keystone placement. He checks every measurement 3 times. He watches as the wooden supports are carefully removed, holding his breath, waiting to see if the arch holds. And every time, miraculously, it does. The semicircular design works perfectly. The weight distributes evenly. The stone locks together. 3 years into construction, The first section of arches is complete. They stand like giants, marching across the valley, 27 meters tall, perfectly aligned. On top, the water channel rests, lined with opus sinonium, ready to carry water. Quintus walks beneath them, staring up. The scale is overwhelming. These arches will stand for 1,000 years, 2,000. They will outlast the empire itself. Long after Rome falls, these arches will remain, puzzling future generations who will wonder how primitive people, without modern technology, could build something so perfect. But Quintus knows the secret. It is not about technology. It is about understanding stone, understanding weight, understanding how forces flow through structures. The Romans have mastered these principles through trial and error, through failure and success, through the accumulated knowledge of generations of engineers like Nonius, who came before, who solved the impossible problems, who figured out how to move water across mountains and valleys using nothing but gravity and stone. The Aqua Claudia is completed in 52 AD. It delivers 190,000 cubic meters of water to Rome every day. Combined with the other aqueducts, Rome now receives over 1 million cubic meters of water daily. That's 1,000 liters per person per day. More water per capita than most modern cities. The water flows to public fountains, to baths, to toilets, to private homes. Rome becomes the cleanest city in the ancient world. Disease rates plummet. Life expectancy rises. The population explodes to 1.5 million people. All because engineers figured out how to move water, how to harness gravity, how to build in stone. But this golden age will not last forever, because empires, no matter how strong, eventually fall. And when Rome falls, the first thing to die will be the water.
537 AD. Nearly 500 years after the first aqueduct was built, Rome is under siege, but not by a traditional army. The Goths, led by King Vitiges, surround the city. They have tried to breach the walls, failed. Tried to starve the city, failed. Rome's walls are too strong, its food stores too deep. But Vitiges realizes something the Romans have forgotten. Rome's true strength is not its walls, it is its water. One night, Gothic warriors approach the aqueducts outside the city, not the parts inside Rome's defenses, the sections in the countryside. The arches, the tunnels, the vulnerable points where water flows unprotected. They carry axes, hammers, iron bars, and they begin to destroy. They smash the arches supporting the Aqua Claudia. The stone that took years to build crumbles in hours. They block the tunnels of the Aqua Marcia with rubble. They cut the lead pipes of the Inverted Siphons, releasing thousands of liters of pressurized water to flood uselessly into the valleys. By dawn, 6 of Rome's 11 aqueducts are destroyed. The water stops flowing. Inside Rome, citizens wake to find their fountains dry, the public baths empty, the toilets backed up. At first, people do not panic. They assume it is a temporary problem, a blockage, a maintenance issue. The engineers will fix it. But the engineers cannot fix it because the damage is outside the walls, in enemy territory, unreachable, irreparable. Within 3 days, the water crisis becomes desperate. People begin drinking from the Tiber again, that same Tiber that is now more polluted than ever, filled with sewage from 1.5 million people. Disease spreads immediately. Dysentery, typhoid, cholera. The public baths close. Without flowing water, they become stagnant pools breeding disease. The great bathhouses that defined Roman civilization, that were the center of Roman social life, sit empty and dry. Within a week, the smell becomes unbearable.
Without water to flush the sewage system, waste accumulates in the streets. The city that was once the cleanest in the world becomes a cesspool. Everything the aqueducts prevented returns with vengeance. The Roman commanders realize the catastrophe. They send soldiers to try to repair the aqueducts, but the Gothic forces control the countryside. Any repair party is attacked, killed. The aqueducts remain broken. Vitiges waits. He does not need to storm the walls. He does not need to fight. He just needs to wait. Wait for disease to do what armies could not. Wait for Rome to destroy itself from within. By the end of the first month, 10,000 Romans are dead from disease. By the second month, 30,000. The population that swelled to 1.5 million because of water now collapses because of its absence. People flee the city. Those who remain grow weak, desperate. Civilization crumbles when the water stops. The siege lasts a year. When it finally ends, Rome is a shadow of itself. The population has dropped to 500,000. The great baths never fully reopen. Many of the aqueducts are never repaired. The knowledge that built them is already being lost. Over the next few centuries, as Rome declines and falls, the aqueducts fall with it. The maintenance stops. The settling tanks fill with sediment and are never cleaned. The opus signinum lining cracks and is never repaired. Sections collapse. Trees grow through the channels. The water stops flowing. By 800 AD, Rome's population has fallen to 30,000. The city that once held 1.5 million people is now barely a town. Most of the aqueducts lie in ruins. The knowledge of how to maintain them is forgotten. The Dark Ages have begun. But the aqueducts themselves remain, broken, overgrown, silent, but still standing. The arches of the Aqua Claudia still march across the Roman countryside. The tunnels carved by Nonius Stuus still run through the mountains. The inverted siphons, though no longer functional, still demonstrate the physics that made them work. 2,000 years later, modern engineers study these ruins. They marvel at the precision, the gradient maintained over 90 kilometers, the arches that still stand after earthquakes destroyed newer buildings, the opus signinum lining that remains waterproof after 2 millennia. And they realize something profound. The Romans did not conquer the world with legions. They conquered it with engineering, with the ability to bring water to cities, with the knowledge to build in stone structures that would last forever. The aqueducts were not just infrastructure. They were the foundation of civilization itself. When the water flowed, cities thrived, art flourished, culture advanced. But when the water stopped, civilization collapsed, darkness returned. Because, in the end, empires are not built on swords. They are built on water, and they fall when the water stops flowing. The Roman aqueducts still stand today, not as functional systems, but as monuments, reminders that the greatest achievements of humanity are not weapons or palaces. They are the systems that bring clean water to people, the invisible infrastructure that makes civilization possible. And buried in those ancient tunnels, in the precise gradients and waterproof linings, lies a lesson we are still learning: that water is life, that engineering is civilization, and that the true measure of a society is not how tall it builds, but how well it serves the basic needs of its people. Rome fell, but the aqueducts remain, teaching us still.